So, we'd like to start thinking about how to more rigorously measure the evidence against the null hypothesis. And the tool that we're going to use is p-values. So let's go back to our example, the experiment run by the shoe brand Atheist, where they noticed that their packages were taking a long time to arrive, and they thought that it might have to do with the Atheist branded tape that they were putting on their packages. So they sent out 178 packages, two each to 89 people. One package had the Atheist tape, the other one had plain tape, and then they tracked how long it took for these packages to be delivered. Remember, our response variable is the days to delivery, and the explanatory is the type of tape. And our question is basically, does the type of tape impact the time to delivery? So we're going to formalize that into some hypotheses. I don't know why they showed up in the middle of my slide, but here we go. So our null hypothesis is going to be that the average amount of time for the branded tape is equal to the average amount of time for the plain tape. And the alternative is the mean for the branded tape is not equal to the mean for the plain tape. Or we could rewrite this by doing the subtraction. Mu b minus mu p is equal to 0, or mu b minus mu p is not equal to 0. So here's some data about the amount of time it took the different packages to arrive. So you can see we've got the plain tape and we've got the branded tape. And it looks like the median, the number of days for the branded tape, is slightly higher than the median number of days for the plain tape. But there's also a lot of variability here, right? The middle 50% overlaps a fair amount with the middle 50% here. The boxes overlap a ton. So if I looked at this visually, it's hard to tell. Are these two things really different? They look a little bit different, but are they different enough for us to have a lot of evidence against the null hypothesis? And I could look at it another way. I could say, okay, my X bar for the branded and my X bar for the plain, and the mean is 13.79 days versus 10.75. I could do this X bar B minus X bar P, the 13.79 minus 10.75. Which is 3.04 days. So it's taking, the average was 3.04 days more for the branded tape than the plain tape. That's what we observed in the real data. So why would those means be different? There's sort of two different things that could be happening. One is that the alternative hypothesis is true. It actually takes longer for the Atheist branded tape packages to arrive. And we're not saying we know why that is, but that it's actually taking longer. And then the other option is that the null hypothesis is true. And this would mean that just randomly, the package that were going to take longer got assigned to have branded tape. And so just by random chance, the ones that had the branded tape took longer to arrive. And our goal is to determine whether the null hypothesis is a plausible explanation given the sample data that we observed. So what we want to see is what sorts of statistics could we get if the null hypothesis were true. And one way to do this is to think about how the actual experiment was run. So in the actual experiment, they started off with a bunch of packages. I think I have 12 packages here in my picture. In reality, they had 178 packages. And then you randomly split the packages into the two groups, the treatment group and the control group. So the treatment group has the Atheist branded tape. The control group has just plain tape. And then you have controlled the explanatory variable, right? You've put the different tape on the two different boxes, and then you're going to observe the response, how long it takes for them to arrive. So again, this is just a little mini version of the experiment, but in my picture, I've got 6 boxes that were in the treatment group and 6 boxes that were in the control group. And I can see this box took 13 days to arrive. This one took 11, 15, 18, 12, 8, 8, 7, 15, 11, 11, 9. So we could compute the average, the X bar for the branded tape and the X bar for the plain tape. I already showed you those means for the full data set, but let's do them for these mini data sets as well. So for this little mini data set, it took on average 12.8 versus 10.2, and I could do my X bar B minus X bar P, 12.8 minus 10.2, just for those 12 boxes, and they were 2.6 days different. Okay, so this is the real experiment, the real data, and I could have done this with pictures of 178 boxes, but just for simplicity, I'm showing you just a few boxes. And the way that we are going to see what the world would be like if the null hypothesis were true is we're going to run a simulation. So we're going to take those boxes and the observed amount of time that they took, and then we're just going to say that those become our original data set. So the way that I've represented it here are just plain boxes with no tape on them, but I've put the same number of days that it took. So the 13, 11, 15, 18, I put those here, and then I've got the other 6 here. And what we're going to do is we're going to re-randomize the packages into groups. So I'm just going to use the computer to randomly put some of them into the treatment group with the scare quotes around it, and I'm going to randomly put some of the other ones into the control group with the scare quotes around it. So now here are some amounts of times that the treatment group took, and here are some amounts of times that the control group took. And again, we could compute our X bar B and our X bar P just from that little mini data set. So for this one, I got 12.7 and 10.3 was pretty similar to my original numbers, but I could repeat this many times. So I could randomly put them into the treatment, quote unquote, and control, quote unquote, groups again, and then look to see X bar B, X bar P, and this time I got an average of 11.5 and 11.5. So there wasn't a difference in means this time. They were exactly the same mean. And I could randomly reassign them again, find the means, find the difference in means again. So this is a way to build up a distribution of what statistics could look like under the null hypothesis.